Hey, welcome back. Today we're going to talk about lesson 7.1, day 1, and we're going to look at what it means to take a sample of scores from a population and try to figure out what is a reliable sample and how does it relate, how does a sample mean relate to the mean of the population. So here we go. Let's just say we've got the situation here. So we want to know how the Chapter 6 test went. So we take a sample from a population. So the population will be all the scores. So we use the average from the sample to estimate the average of the population. That makes sense, right? So if we want to figure out what's the average age of juniors at school, we would take maybe a couple of them, a handful, a class, and try to figure out, okay, the mean of the class, how does that relate to the overall mean of the class, or the overall mean of juniors, let's say, in the United States. So let's start with a simple example. The fifth hour was very small. There were only 4 people that took the Chapter 6 test. The scores were 60, 70, 80, and 90. Okay, so we're going to illustrate this principle in a very simple way. So let's just say for a second, we want to make a dot plot. So I'm going to draw my line here. Got to grab my pen tool. There we go. And let's make a dot plot here. And I've got to label my dot plot. So 60, 70, 80, 90. And I'm going to put my dots on here. So I've got one at 60, one at 70, one at 80, and one at 90. All right, so we're going to label it population distribution, right? Because this is all the scores. This is the population distribution for this class. So what does each dot represent? And this is going to be important as we start to take samples and things like that. This is one individual score. I know that seems elementary, but it's important when we start to pull out like a sample from a population. It can get confusing, like what does one dot represent? And so in this case, this represents one score, one individual score of 90. Okay, one individual score of 90. So take a sample of any 2 of the scores. So I'm going to pick 60 and 70 and find the mean. So the mean, X bar, is equal to 65. Now, is that the mean of the population? No, that's called a sample mean. X bar is going to be used to represent a sample mean. And that's important because the sample mean in this case might not even represent the mean of the entire population. A lot of times it doesn't. But how close it is in proximity is going to tell us how good of a sample it is, perhaps. Okay, so figure out all the possible sample sizes of size 2. So we could do 60 and 70, 60 and 80. We could do 60 and 90. We could do 70 and 80. We can do 70 and 90. And we could do 80 and 90. Okay? And if we figure out the mean for each of these, and you can see why we picked these. So I pick a small sample, I picked a small example, very simple example, so we can easily find these and compare. But you can easily see here that our sample mean for each of these is different. And since we know the entire population, we're going to be able to compare it pretty simply. So obviously the mean of these 2 is 65, the mean of these 2 is 70, the mean of these 2 is 75. The mean over here, X bar equals 75, X bar equals 80, and X bar equals 85. So which of these, so let's make a dot plot here, and we're going to answer the question, which of these most accurately represents the actual mean. So let's make a dot plot here. I'm going to label 65, 70, 75, 80, 85. And you can hopefully, if you're predicting a little bit here, we've got 2 dot plots in this problem. And our dot plots represent 2 very different things. 80, 85. And on this dot plot, let's point out, what does a single dot mean? Well, in this case, a dot is the mean of a particular sample. Okay, so this is one sample of 2 with a mean of 85. And maybe you see how confusing this could be. So you've got to really pay attention to what is the dot plot representing? Is it representing all the scores? Is it representing the population? Is it representing the sample scores? Or is it representing the mean, or a set of means from a set of samples? That's what I meant to say. So this is called a sampling distribution. And it's called a sampling distribution because this is an array of samples. So a sampling distribution of X bar, because X bar represents sample means. Okay? Now, when we compare that to our actual mean, so the actual mean of these things is going to be called, the mean is equal to, and we're going to use this symbol here, looks like a U, and it's going to be 60 plus 70 plus 80 plus 90. Our actual is going to be the sum over 4, and it's going to be 75. And so when we come down here and we mark our actual score, so that's the mean of our population, right? So the mean of the population would be all the scores, 60 plus 70, and I could have done this down here, right? Plus 90, and over 4 is equal to 75. And that is U, and this is the population mean. And we're going to draw it in on here. It's at 75. This is an important measurement to put on there. So on the sampling distribution of the sample means, I'm going to put on there the actual mean, and that's going to help me compare my different samples to the actual mean. So what are we doing with this? Here's the important ideas of the day. Okay? We're talking about parameters and statistics. And you're like, well, we're already talking about statistics. Parameters and statistics are used to talk about specific types of data. So are we talking about something that's describing the mean, or describing a sample, or are we talking about something that's describing a population? A statistic is a number that describes a sample. For example, we used X bar to describe samples up there, so X with a bar over the top. A parameter is a number that describes a population. For example, when we talked about the mean, that was the mean of the whole entire population. Okay, so let me make a little chart here. Parameters, statistics, and we're going to be talking about a couple of different things here, and you're going to see how this chart plays out. This line actually plays in kind of nicely, right? So for means, the parameter, and I'm going to actually fill this chart. Parameters would be, that's my U. The sample mean, a statistic, would be the X bar. For my probability, P, and this is going to be a P. I'm actually going to move it down. Go back and move this down. So this P with a hat over it. Oh, probability. I wrote probability. This should be proportion. Proportion. So the proportion of a parameter is the proportion of the entire population. The proportion of a sample would be P with a little hat over it. P hat. Looks like a little hat. And then if we talk about standard deviation, The standard deviation of the parameter, so for the population, is what we've been doing. Standard deviation for a given sample is going to be a lowercase s. Okay, and so when we pop over here, our second piece of information that we're looking at today is talking about sampling distributions. And with sampling distribution, they show the statistic found in all possible samples of size n. So what we did up top, when we took all possible samples of size 2, we made a population distribution, or sorry, a sampling distribution of all of those samples of size n. And so our sampling distribution might look something like this, right? Sampling distribution. And I'm going to draw in a model sampling distribution. So we're going to have a bunch of data values here, right? And what do those things stand for? What do those individual little dots stand for? Well, this little dot here, this mark here, stands for a statistic from one sample. Okay, so it's not one individual score, it's a statistic from one score. So what are the types of things that we could, what are the things that we can measure? So we could do a sampling distribution of the means, which is what we did above. We could do a sampling distribution of standard deviations, which is what would that look like, right? It'd be all possible, and that's the key. It's all possible samples of size n. And so you distribute these and you see, given the fact that we have all these samples, every possible sample of size n, what would be all the means displayed in one data chart? What would be all the standard deviations displayed in one data chart? And so a sampling distribution shows all shows all samples of size n, whereas a population distribution shows all individuals. Okay, sampling distribution, and it's called sample, it shows samples. Population distribution shows each individual value. So let's do a little check your understanding here. One of the ways you can do this, since we're on a video, is you can pause it right here and try to do this by yourself, and then unpause it and check your answers, or you can just follow along with me. So here's the question. To determine how much homework time students will get in class, Mrs. Lynn has a student conduct a simple random sample of 20 chips from a large bag, not potato chips, but like bingo chips. The number of red chips in the simple random sample determines the number of minutes in class that students get to work on their homework. Mrs. Lynn claims that there are 200 chips in the bag and that 100 of them are red, so 50% are red. And when Jenna selects a random sample of 20 chips from the bag without looking, she got 7 red chips. Does this provide convincing evidence that less than half of the chips in the bag are red? So basically, Mrs. Lynn says there's 100 out of 200 that are red in the bag. And so people in the class are probably thinking, oh, if she pulls out 20, we're going to get 10, right? That's what we think. So it's a 50% chance. There should be about 10. Well, she pulls out 7. And so somebody might claim, well, there's only 7. Like, there should be 10. Maybe there's not as many red chips in the bag as she said there were. And so is it convincing evidence to say that this is, that there's not 100 red chips in the bag? So what's the population here in this scenario? What's the population of this bag? So it'd be the 200 chips. And so the sample would be the 20 chips that Jenna pulled, right? And so the parameter would be, so my population, my proportion would be that I'm looking at the 100 out of 200 that are actually red, that Miss Lynn claims are red. Our statistic is from the sample that was pulled. And so that's p hat. So our sample would be 7 out of 20, which would be 0.35. So we're actually going to be comparing this 0.35 to this 0.5 to determine, is it convincing evidence that Mrs. Lynn didn't have the 100 chips in there, okay, or that something else went wrong. So what's the evidence that less than half of the bags and the chips are that less than half of the chips in the bag are red? The evidence is the sample seven of 20 red chips. So that's less than 50%. Yes. So our evidence is we pulled the sample. It's less than 50%. Is it convincing though? Let's look. Okay. So provide two explanations that the evidence described in part A. So what's the two possible explanations? We got either we got 7 purely by chance, right? So maybe it just happened. Or there are less than 50% red in the bag. Right? So this happens and we go, either, man, that doesn't have 100 red chips in it, or, well, I guess we just by chance it happened. So how are we going to test this? We're going to run a sample. So here we go. We're going to run a simulation. So we use technology to simulate choosing 500 SRS of size 20. So this population distribution, or this sample distribution right here represents 500 samples of 20 if there's 50% red. So there's 100 red, 100 blue in this digital bag, right? We did 500 samples. So the dot plot shows that p hat, the sample proportion of red chips for each of the 500 samples. So this right here, there's one dot on the graph at 0.8. So what does that mean? That value, if this is a sampling distribution, this represents one sample of 20 chips. And it had 16 red. Why 16 red? Because 0.8 is equal to 16 out of 20. So this dot, it's important this dot represents a sample of 20 chips. It had 16 in it. Okay? So that's the answer over there. C graph. So would it be surprising to get a sample proportion of p hat equals 7 of 20.35 or smaller in an SRS of size 20 when p equals 0.5? Justify your answer. So let's look. We're looking to compare what happened in our one sample to this population distribution. Check it out right here. Boom. No. 35% red. Many times. Okay, it actually happened many times. And so it's not sitting out there at the end. It happened many times. So based on our previous answer, is there convincing evidence that less than half of the chips in the bag are red? Explain your reasoning. No. There's a large enough chance that we get a sample proportion of 35%. So there is a large enough chance that we get 35% or less, right? So all this over here, 35% or less by chance, because it's like greater than 5%, right? We have quite a few samples over here that fit in that 0.35 or less, certainly more than 5%. Okay, so that's the basic gist. Make sure you keep population distribution and sample distribution straight and what each individual stands for on those dot plots. Make sure you understand exactly what that means when you go into it. Okay, thanks for watching, guys, and we'll see you next time. All right, welcome back. So today we're going to talk about using samples and parameters to describe statistics and how reliable are they. So, as you can imagine, when you're taking different samples from a population, you've got different size samples, you've got different representative samples. And so how do you know if it's good or bad, or if you have a good sample that represents everything in the population? So let's talk about a little bit of what that process might look like. First of all, what we want to do is we want to find something called an unbiased estimator. Because ultimately what we're doing with a sample mean or a sample standard deviation is we're estimating the statistics, or statistic is the wrong word in this context, but the statistic of a population, right? If we want to know the mean age, does our sample actually represent the mean age of the population? And so that would be an unbiased estimator. So we find a sample and we're going to find out, is it unbiased? And so what we do is, we're going to say this: a statistic is unbiased if the mean of a sampling distribution is equal to the parameter. Okay, so when we look at it, our distributions can tell us something. And so, when we've got this sampling here, and let's say our mean is right here, and we've got a bunch of, data points, and they appear, they're starting to take on this normal shape, we would call this unbiased, right? So our samples our sampling distribution comes to this, starts to look like a normal deal. That's how we know it's going to be unbiased. Well, how do you know if it's biased? Well, you look at your sampling distribution here, and your mean is not in the middle. It's like way over here, and it's skewed. And we end up with, something that looks sort of this way, And so this is going to represent something that is biased. And so the closer that it gets to this normal looking curve, the closer we're going to be to something that's going to be an unbiased estimator. Well, what are we doing? How do we do this? How do we make sure we have representative samples? Well, honestly, there's some parameter like a population. You may never get everybody, but if you increase your sample size, right? So instead of asking 5 people, you ask 100 people. That's going to decrease the variability in the statistic. What do I mean by that? So let's say you take a random, so there's 1,000 tests out there. Okay, so 1,000 people took the SAT or the ACT, and you take samples of size 3. Okay, so you take a ridiculously tiny sample based on a lot of data, and your sampling distribution looks something like this, right? So you start to take these sample sizes of 3, and you got one that's over here that's close to like an 18 or whatever, and you got a 36 over here. We'll just kind of randomize this. So, and you take one, and you get 3 people who did really well on it, and then you've got here's another one, and they're sort of like these samples of 3 are sort of all over the place, and they're like kind of bouncing around. Well, you can see how if you've only got a sample size of 3, if you get 3 low ones or you get 3 high, like you've got all this variability because the data doesn't have a chance to kind of clump together. Where if I take samples of 100 from a population of 1,000, then they're going to start to fill in here, right? Because you're going to have more of these that kind of drive it to the middle. And so I'm going to end up with something that looks a ton more normal because I've got more data that's pulling itself together, right? So this is kind of what we talked about with that mean and median when, like, what do you use in a certain situation? Well, if you've got a lot of data that you can pull from, you can push that graph to the middle and make it more normal. If you've got sample sizes that kind of even each other out, right? You pull a low one, but it's okay. I've got an opportunity to pull a higher one here, and they kind of push themselves to the middle. So let's do a little checking understanding. There's a histogram to the left. It shows the interval time in minutes between eruptions of Old Faithful geyser for all 222 recorded eruptions during a particular month. So this is 1 month, and for this population, the median is 75 minutes. So if it's all 222, what they're saying is the population is based on this month, and there's 222 of them. So let me draw in this median here. Important that this is not mean, but it is median, right? So my median is right here on the graph. And I'm going to put population median and is equal to 75. Okay, so the population median is equal to 75. And so on the right, we have a simulated sample median interval time in minutes. So we use technology to take 500 random sample sizes of size 10 from this population of 222. So the 500 values of the sample median are displayed in the histogram at the right. The mean of these values is 73.5. So here's what we're doing, right? So they took these 222 eruptions. They took sample sizes of 10. So think about that. So 10 out of 222. They took 500 different samples. And they drew the sampling distribution on the side here. We'll check it out. If I ask you to describe this, let's say that the quiz or test asks you to describe this, you're going to say that it's skewed left. We've got a tail to the left. And so where's my median? Where is my mode? And so what we've got here is an opportunity to compare these two things, all of the eruptions and the simulated sample median interval in minutes. So think about it like this. So label this sampling distribution of medians. So these are sets of 10. Right, so these sets of 10 here. Those sets of 10 give us an opportunity to pull like a bunch of different types of samples. So, is the sample median an unbiased estimator of the population median? Justify your answer. Well, think about it like this. If we have a sample median and the population median, what we said up top was they don't match. So we'd say no, the mean of the sample medians 73.5 is not the same as the population median. Okay, it's not the same as population median, so we can't say that's an unbiased estimator because it's not the same. It didn't match. We didn't take large enough sample sizes or whatever. So suppose we'd taken samples of size 20 instead of size 10. Would the variability of the sampling distribution of the sample median be larger, smaller, or about the same? So what we can say is the variability, so the sample size goes up, so the variability decreases. I mean, think about it. It's like that example I gave you at the top of the ACT scores. If you take smaller sample sizes, the variability is going to be greater within it, right? If you have 20 instead of 10, you've got scores that are kind of evening each other out and bringing everything to the middle. So describe the shape. This is exactly what I was talking about. The shape is the distribution is skewed left. With a single peak at 75, sorry, between, so there's a single peak between 75 and 77.5. between 75 and 77.5. Okay, so that's all there is to it. So when we're looking at these things, we are evaluating, is it an unbiased estimator by comparing, is it the same as the sample the same as the population? All right, guys, thanks for tuning in, and we'll see you next time.